Good afternoon. This is Professor Nathan Weezy of Marquette University, and in this section we're going to talk about continuous control part 2. And this whole section is mainly going to just focus on transfer functions and what their Bodie plots will look like. Okay, so we're going to start off really simple, and then we'll expand on more difficult examples. So the first thing we're going to look at here is, if you look at this transfer function, this is just a straight gain. It's a gain of 4. Now, when we go ahead and Bodie plot this, what we usually do is calculate the gain. Well, first of all, the gain here is fixed. It's 4 for all frequencies, so it's going to be 4. But generally, the Bodie plot is in dBs. So what you're looking at is a 20 log 10 of 4. And in that case, that comes out to be somewhat better than 12, as you see this straight line here in our Bodie plot. So this is a really simple one, right? I mean, it's probably about the simplest transfer function you're going to get. Now, the next part is, in general, we also calculate the phase of the transfer function. Now, as you can see, you look at this transfer function, it is going to be 0 for all frequencies because it's just a constant 4. It doesn't have any angle that changes with respect to frequency, or in other words, the angle is 0. So if we scroll down here, you can see that our phase is indeed 0 for all frequencies. Okay, so that was a really simple one. So this is the Bodie plot. We usually look at gain and phase of a transfer function. Now, let's go to a more complicated example. All right, here we have one of our favorite transfer functions, the integrator. So if we put this in as a complex number, it'd be simply h of j omega. Right now, as you can see, the gain of this thing, if we take the gain of this, we're simply going to have 1 over omega as we sweep frequency. So this is why you see a straight decreasing line for the magnitude. Now remember, this is the gain without it in log or in magnitude, so you actually need to write 20 log 10 1 by omega. That's actually going to be your gain in dB, okay? And that's why this actually turns out to be a straight line with a slope of minus 20 dB per decade. So what's a decade? Well, that is an order of magnitude and frequency. That would be these lines here. So like, for instance, this is 10 hertz. This would be 100 hertz. From this point to this point, this drops approximately 20 dB. And you can look at it here, because on the left-hand side, we have 20 dBs per each line or decade. And you can see we're dropping about 20 dB per decade as we go down. Okay, awesome. Now, the other thing is, what is the phase relationship of the integrator? So we know that it rolls off at minus 20 dB per decade as we go up in frequency, but how does the phase roll off, or what does the phase look like in this one? So now what you're going to want to do is calculate the angle of this complex number as you sweep omega. Okay, great. So we can move the j upstairs, and we'll get something that looks like this. So as we sweep frequency, we get something like this. And now this right here is a complex number. The one thing to note is the angle of this complex number is always fixed. It's always at minus 90 degrees, regardless of what j omega is, rather. So it's a complex number that is literally just pointing straight down. So it's always at minus 90 degrees. So as we look at our phase plot here, this is why you see a straight phase relationship across frequency, minus 90 degrees. And that right there is the integrator. Okay, let's go to a more complex example and start to build upon this. All right, check out this example. Here's our transfer function. This ought to look pretty common. In this example, I gave it a number so that we could focus on calculating the gain and phase of this, so the Bodie plot. But if you look at this, this looks very familiar. We essentially have a 0 transfer function. This is just 0. Okay, cool. So let's go ahead and calculate the gain. All right, so we plug in j omega for s. That'll lead us to this part here. And now we have a complex number. We have this 1 plus j omega by omega z. And we're sweeping omega. We're sweeping this omega here. So essentially, this is a complex number. You can square the real part and the imaginary part and take the square root. That would be this. And you can solve it for here. If you do this, this should be the gain. But what you want to do to get it in dB is take the 20 log of this, 20 log 10 of this, and you will get your phase relationship. Now, sorry, your gain relationship. Now, what's interesting is, before you hit this omega z, which in this case is 62.83. Before you hit that, essentially what happens here in the gain is that this number is quite small, omega, relative to 62.83. So what happens there is that essentially you have a gain of 1 squared square root 1 at low frequencies or frequencies below 62.83. And that's in radians. So if we look at that here, that translates to about 6.2 hertz, somewhere right about here. So you can see in our gain plot, we have a gain of 1, so 20 log 10 of 0 is 0 dB, excuse me. This right here is 1, a gain of 1 or 0 dB, and then we start rolling off at, or increasing at 20 dB per decade when we hit that 0. So this is plus 20 dB per decade. And that's all due to now this term will start to dominate after you go past that pole, or the 0, excuse me. Now, how about phase? What happens with phase? All right, that's an interesting one. Essentially what we can do is plug in, we could try to take the angle of 1 plus j omega over omega z as you sweep omega. And of course, this is a complex number, so what you want to do is take the tangent inverse of the imaginary over the real. So we have omega over omega z over 1, so that's what we get here. And of course, as we plugged in omega 0 z, or the 0 here, and so this function right here is what you get for the angle as you sweep. Now, what's interesting is at really, really low frequencies, as omega is close to 0, you're essentially taking the tan inverse of 0, which gives you 0. That would be this part. When you're at really high frequencies, you're essentially omega is going towards infinity. You're taking the tan inverse of infinity, which is about 90 degrees. That's this area. And then somewhere about a decade above and below this 62.83 is where you start to see this transition region happening. So that would be from like here to about here. And what will happen in this, in a straight line approximation sense, is you'll get about 45 degrees per decade increase because of a 0. So for instance, if we looked from here to here, again, this is a straight line approximation, that's about 45 degrees in 1 decade from here to here. And then another 45 degrees from 10 to 100 hertz. And that's a straight line approximation. Again, I made these in MATLAB so you can get the actual thing, but just to give you an idea what a 0 does, essentially you're going to add 45 degrees of phase right where the 0 is, and it's going to increase your phase by 45 degrees per decade, 1 decade below the 0 up until 1 decade above the 0. This is what you always get when you have a 0. Let's calculate now the Bode plot for this transfer function. If you look at this, we now have a 0 in the denominator, which we call a pole. It means as we hit that, the gain is of that particular pole is going away. Okay, so let's take a look here. If we go ahead and substitute for s equals j omega, and go ahead and try to calculate the gain of that complex number, it goes to this equation here. Now up top the gain is 1 because it's a constant. In the bottom we have a real and imaginary, so we can take the square of both of them and the square root, and we'll get the magnitude, and we'll end up with this. And if we take the 20 log 10 of this result, we will get the gain in dB. The one thing to note here is that essentially when omega is really small, meaning it's small relative to 62.83, this number is essentially 0, which means that the gain here is 1, and if you take 20 log 10 of 1, you get 0, and that is this region right here. Okay, and this is where omega is much, much less than 62.8. Now, once you get essentially hit 62.83, then this factors into the gain. And what happens is you start to drop off at 20 dB per decade. You get this nice straight line like this. And this is the opposite of a 0, where that increases at 20 dB per decade. This one will drop off at 20 dB per decade, which you can see from, for instance, from here to here. This is 1 decade. You drop 20 dB. Okay, So that is the gain in terms of a single pole. And if you look at this, this is very commonly referred to as a low-pass filter, right? We can pass all these frequencies here, and then we start rejecting them after that point. Now what happens to the phase? If we go ahead and look at this equation here, again, now we just need the angle of that complex number. Well, up top, essentially, we don't have to worry about that because there is no angle to that. But let's just do some simple algebraic manipulation to get the right angle here. So if you multiply the top and bottom by the complex conjugate, what we've done here in this step, you realize in the bottom, that is just a gain. So we can pull that out front, and then you just have a complex number up top now. And then you could take the tan inverse of that, which we do in this step, and you can see this looks very similar to the angle of a 0, except for now we have this minus sign in there. So when you have a really small omega, when you look at this, essentially what happens is you're taking the tan inverse of 0, and of course what you get is 0. So this right here is omega is much less than 62.83, right? Now, when you go to really high omegas, much greater than 62.83. So it's much greater than 62.83. You're essentially taking the tan inverse of infinity, which gives you minus 90 degrees. Well, sorry, it's the tan inverse of minus infinity, which gives you minus 90 degrees. And then you have this transition region. Starts about a decade above and below where the pole actually is located. Okay, so if we look at the pole here, this is the pole. 10 hertz, that's 62.83 radians. About 1 decade above, so say 1 hertz, and 1 decade above, at 100 hertz, you get this minus 45 degree per decade drop off, only for 2 poles, starting 1 decade below the pole and ending 1 decade above the pole. Okay, and that's commonly referred to as the straight line approximation. Of course, if you don't follow this, you can simply just sweep this tan inverse here and you will get your proper angle. Okay, for any arbitrary frequency. All right, let's do another more complicated example here. What we have now, if we look at this transfer function, is we have a 0 up top, and we also have a pole at the origin, because s can equal 0 in the denominator. That's at the origin. So what we're going to go ahead and do is just rearrange this like this with some algebra so that we can calculate the gain and phase of this. So replace s with j omega, and then calculate the gain or the magnitude of the complex number and the angle, and then we can get our Bode plot. All right, if we go ahead and do that for the gain, what we'll end up with is this. And what you're going to see is at really small omegas, this term up top essentially is 1. And the bottom, the number on the bottom will be omega. So 1 over omega, if you recall, that was what the gain was for 1 over s. So that was this one right here, dropping off at minus 20 dB per decade. Okay, and then once we hit where the pole is in this, or sorry, the 0 in this case, which is again 10 hertz. This is where our 0 is in this case. This term will start to come into play and roll it back up, and you'll get something flat. Okay, you'll get something flat. So the gain will roll off and be a flat number. That would be this region here. All right, now we can also calculate the phase of this by just calculating the angle of the complex number. Up top you have a complex number, and in the bottom you have a complex number here. One thing I'll say about this is we can use a trick of tan inverse. So if you have tan inverse of a over b, you can do tan inverse of a minus tan inverse of b, which is what we're doing in this step. This is just a trig identity. But what you get on the bottom is, since this is always j omega, that's always minus 90 degrees. And then you have this term, which is swept over omega. So what happens at really small omega is this term is 0, but what you get from this minus right here is minus 90 degrees. So essentially at really low frequencies, omega close to 0, you start at minus 90 degrees. At really high frequencies, then you can see that this tan inverse will be 90 degrees. So 90 minus 90, you'll essentially roll back to 0 degrees on your phase plot. So this is much, much greater than, in our case, whoops, let's just write it as omega z. And over here, this is omega much, much less than omega z. That would be that region. And of course, in between those two, 1 decade below the 0 and 1 decade above, we essentially have this transition zone where we're going to, in this case, increase at 40 dB per decade. Sorry, 45 degrees per decade. And again, this is a straight line approximation. If you don't like this, you can simply plot it by just calculating the individual angles at each phase. Okay, and this was just a simple introduction to calculating gain and phase of a Bode plot. Let's do one more to finish it up here. Okay, let's look at this one. This is a pretty complex now. You can see we have 0 up top. We have a pole, 2 poles in the bottom, one at 0 and another one at 6283, as you can see here. All right, so let's take a look at this. Again, replace S with j omega and calculate the magnitude. That's how you're going to get the magnitude part of the Bode plot. And you follow along the math here. We'll go all the way to the end, 20 log 10 dB. But what you notice here is the first thing is whenever you have a 0, when omega is much, much less than either one of these two frequencies, you're essentially going to have just that integrator, or 1 over omega, which is what you're seeing in this section here. This is due to the 0 at the, a pole at the origin. So this is minus 20 dB per decade. Then what happens is if you look at the frequencies, so we have a 0 at 6.28, we have a pole at 6283, and we also have another pole at 0. So we start off with a minus 20 dB per decade because of that pole at 0. Then if you look, we hit a 0 at roughly 6.28, which is 1 hertz. And guess what? The gain will start to flatten off. All right, so you'll get this region right here. And then lastly, what will happen is once we go to 6283, which is in this plot about 100 hertz, we'll start rolling off again at minus 20 dB per decade. That would be this region. So this again is minus 20 dB per decade. Okay. This is 6.28 omega equals, this was our 0, this is omega p equals 6283 right at that point. Okay, and that's the gain. Now let's talk about phase. Again, we're just going to calculate angles of complex numbers in this step here. We can use what we learned before to understand what's going on. So we know that at really low frequencies, essentially, if we looked at this thing, tan inverse of this 0 will be 0, this one will be 0, but we have this fixed minus 90 degrees, and that's due to the integrator, or the pole at the origin. So we'll start off here. At really high frequencies, this term here and this term here, well, what's that going to shoot to? That's going to shoot to 90 degrees. So what will happen is we'll have a plus 90, minus 90, and a minus 90. We'll end up right back where we were at the end. All right, so let's plot where our pole and our 0 was, the non-zero one. So you can see we start rolling back up here. We have this omega, this 0 at 6.28. And right about here we have our pole. This was at 6283. So what will happen is, remember, a decade below and a decade above the 0 will start rolling off at, or we'll start increasing our phase at plus 45 degrees per decade. Okay. Then we'll flatline. Nothing will happen during this region until we're about a decade below our pole. So let's draw this here as orange. We'll flatline here. And what happened is 1 decade below, which is about 100 hertz, will drop off at minus 45 degrees per decade. And again, if you don't like the straight line approximation approach, that's okay. You can always go back up here and just calculate it based on the actual angle of the complex number. Okay, so hopefully this was fruitful. Essentially what we want to get out of this is the ability to understand simple Bode plots, how to construct them from a transfer function. Eventually we'll use this knowledge to kind of shape the Bode diagram to be a shape that will be advantageous for us in terms of control. So it's just important right now to really understand from this lecture what does a zero do, what does a pole do, what is an integrator, a pole at the origin, how to calculate gain, and how to calculate phase. All right, thank you.